Okay, so let's kind of talk about number 18, because number 18 kind of ties together a whole bunch of different things. So imagine, you kind of have to visualize this setup, and over the years, I've tried to actually have this setup work, but it actually, the closest I could get was that rail gun, when, you know, when I cranked it up and we made the wire, we made the little piece of aluminum roll and there were sparks, okay? And that took such a tremendous high current to even get anything that was really noticeable. And then it's even worse if you try and use like a pure magnetic field, because that takes a really, really strong magnet. So I've tried to get this to work even with like the strongest magnets that we've got. And you see a little bit of motion, maybe, generally not. So it's one of those videos that works really good in theory. And you can see it, like tomorrow, y'all are gonna do the lab. You're gonna revisit the lab where you have the magnet and moves between the aluminum plates. So that's easier to see, but try and do this, physically do this setup, that's tough to do. But let me kind of paint the picture when I tried to do this. So you've got a loop like this, okay? And then you would have a rod that's conducting, because you have to be able to complete a circuit. And you've got X's, so here's the deal. So when I tried to build this, if you look what's happening on number 18, so the magnetic field is increasing in strength. So here's what's gonna happen. So you have like a magnet, okay? So look at it this way. Here's the plane of the paper, and you want X's. So let's just think this through. You want X's going into here. So if this is the magnet, I want X's going into here. So I want this to be the north end of the magnet, the north pole of the magnet, or the south pole of the magnet?
North pole.
Why?
Because you go from north to south on the outside of the magnet.
Beautiful. So I would want this to be the north end of the magnet, because the field lines is the Confederate designation. You're going from the north to the south. So I would have the north end of the magnet here. This would be the plane of the paper. Imagine the loop is here. I want to increase the intensity of the X's. Alex, do not answer this question. Am I going to move the magnet closer or further away? Closer. Okay. Now, you can make the analogy, and this will be important later on in the lecture, that you can somewhat visualize a magnetic field as like a shower head where you have water coming out like this, okay? So imagine here's the shower head, right? And there's a couple of things that you can do in terms of the intensity of the stream that you feel. And imagine that you have like a bracelet like this that you're holding up in the stream of the shower. Now, when you look at changing a magnetic field, and this is what we're going to be talking about today. So imagine here's the stream of the shower. If this is like the axis coming out like this, obviously I'm going to get the most streams when it's at a 90-degree angle to the stream of the shower, okay? Because if it's parallel with it, none of the water is going to come through. So one option is that I can change the angle of the bracelet in the shower head. Make it right angle to it, make it parallel with it. I can also change the size of the bracelet, because obviously if I have a really, really small ring, okay, hey, there isn't going to be much of a magnetic field going through it. Or I can increase the area, and I can make, if I increase the area, I get more of a magnetic field. The other thing I can do is I can change the physical location of the bracelet, okay? Because if you imagine that shower head, those streams of water spreading out, if I move it closer, what's going to happen to the number of streams that are going through that bracelet? Sydney. Here's the shower head.
It's going to increase?
Yeah. So if I adjust the position, I can change the number of streams that are going through the bracelet. So I want to increase X's. So imagine here's the plane, here's the north pole of the magnet. I'm gonna move it down like this. Mother Nature is going to sense an increase in X's. So what's Mother Nature going to do?
Has to create O's.
Yeah, Mother Nature wants to make O's. So if you're increasing X's, you make more. If you're increasing O's, you make more X's. If you're decreasing X's, you make. If you're decreasing O's, you make O's. So if it's increasing, you make the opposite. If it's decreasing, you make the same. Okay? One of the most vital things that you have to have. Now, here's the other thing. If nothing is changing, and this is his first question on the assignment. If I just have a loop in a magnetic field, and it's just stationary, will there be a current induced in the loop?
No.
No. Something has to change, okay? The strength of the current, the strength of the magnetic field, the location, the angle, something. If everything is static, you're not going to get a current. So, I'm making more X's. So Deacon says I need to make more. So what's going to be the direction of the current not in the wire, but in the bar? What's going to be the direction of the current in there to make more O's?
Must be up.
Up or down?
Up.
Why?
If you use the right hand rule, you're gonna find that the O's are on the left.
Beautiful. So if I use the right hand rule, and my current's going to go up, so that when I curl this, I'm making more O's. So I'm making O's. So the current is going this way. And again, you're only going to see that when you have a change in current. So the current is going up. What's the direction of the external magnetic field? Into the page. So which direction is the force going to feel? To the left. Okay? It's going to be a force to the left. So that's going to try and pull that wire to the left. Connor S.
Thatcher's raising my hand, so how's your day?
Not bad. I hate Wednesdays, but it's not bad.
No, I
So, anyway, so there's your answer to question 18. So then the next part of that, if the magnet is decreasing in strength, so it's just the opposite. So if I wanted to decrease the number of X's, what would I do?
You gotta make
Yeah, I'd move it up. So then, if it's seeing a decrease in X's, Mother Nature is going to make
more O's.
more X's. And everything just gets switched around. Okay? Does that make sense?
see.
Okay. So on question 3, you should have 3 zeros, 1 clockwise, and 2 counterclockwise.
You see two counterclockwise?
You should have 2 counters, 1 clockwise, and 3 zeros.
2A, I have
Okay.
clockwise.
You got 6.
Yeah, I have clockwise.
Huh?
Positive or negative for number 6?
On what are you asking, Connor?
On number 6, when we get there, the sign of number 6. That's my question.
It should be a positive value.
No, it's-
And if it's in millivolts, it would make a really good weighted GPA.
yeah, pretty solid, you could say.
It had to be a weighted GPA.
Really good GPA. Oh, I agree with your answer.
Yeah.
That's right. His answer, I accept it. I think it's in
Yeah, number 5 is an interesting question, but it's gonna be almost like 3 times the speed of sound.
Saber, but you should freeze it a lot
3 times
smaller than
Yeah,
27.
it's been really fast.
It is 9.8. You have to use your FG as your FB.
Okay, now, on number 7,
Wait.
So,
So on number 7, you kind of need to get this visual. So
that's what I.
on problem 7, so delivery truck, aluminum size, is driving west at 75 kilometers per hour, and they gave you the magnetic field. So here's the Earth. Now, within the Earth, where is the actual South Pole in the Earth? Those are south, those are north, right? So within the magnet of the Earth, the South Pole is the North Pole is the South Pole. So which direction do the field lines go around the Earth?
From geographic cells.
Yeah.
They're gonna go up like this, right? So the field lines, so right now, south is that direction. So the magnetic field lines are going this way, okay? So get this visual. Here we are in Mesoamerica, okay? And the field lines are going like this. So field lines coming like this. Here's the truck, right? So here's the side of the truck. And it's moving west, okay? So the field lines are coming in like this. The truck is moving like this, okay? Because that's moving west. So I just want to make sure everybody gets this visual, that the field lines are moving like this, and the truck is moving through that. And it's aluminum, which means that you can move, you can have the charges move. So I just kind of wanted to make sure everybody's cool with that picture. Okay, anything else? Going once, twice? Huh?
Question 5.
Yeah.
Or yeah, problem 5.
Okay. What are the two forces,
Gravity.
No.
right?
This is mine.
So, force of the magnet, so this is gonna be mg, right? Okay? So then, set that up, set that on number 5, which you can find, right? And that's gonna equal,
No, I was just incredibly
Bill.
that I did it right, because I was like, no way, it's 90.
and then, which could also, this is where you're gonna do that v L squared, b squared over r. And then all you have to do is just solve for that value of velocity. There's just kind of an algebra problem.
That would be my guess,
Okay, once, twice,
because that should be.
magnetic field sold. So get that handed in.
So, no return.
.1. That might have been the other.
Yeah, you have.
Yeah, I know, and I forgot to do it, so.
No, we
Yeah.
have actually today, and then we've done learning
I don't know. I said, what you got?
today.
Sean, do you know what?
Wait, what's the
We have a lab. We have a lab.
We have a lab. We're doing a lab.
Isn't that right, Bird?
Yes.
Yeah. See?
We don't listen.
They don't listen. What is going on? I thought you should do the rest of the lab. No, we're doing that tomorrow. Nice, thanks.
With vitamins and antioxidants.
It's a weird planetary map.
It's like a.
No Boba Fett.
It's like a planet with label.
It looks like you can say it's a circuit, but it
It
has
looks like
looks
a
like a
planet
ball
with a really,
It
really
looks like a
big
music
box.
notebook drawn by like a.
It looks like a This is only gonna be
Yeah,
the
that's
generator.
That's my blood.
It's a pool of blood.
It's a pool.
It's a head. It's a head.
It'll make sense in just a second.
It's like a cartoon. Yeah,
He didn't say you were wrong.
Oh, that is a.
I'm pretty sure it's. Oh, I know what it actually is. But I like that better.
Is that like a?
Danny, are we still going?
Yep.
Okay,
Static electricity.
so let me kind of explain what I'm trying to draw in a very three-dimensional way that doesn't turn out well. So imagine this. You have, no, this is not like the Starship Enterprise or anything like that. So all it is a battery hooked up to a wire, and that's going to complete a loop, and you have a switch, okay? So this would be like the top of it. Underneath there, you would have, hold on. What did I do? That was it, okay? So underneath here, you have a second loop. So you have a top loop, we'll even make this more of a visual. So you have the top loop that is hooked up to the battery. And you can close that loop, okay, or that's going to get closed. And then what I want to figure out is what's going to happen to the, will there be a current induced in the second loop underneath it? Okay? Right after it's closed, and then after it's been closed for a long time, and then when we open up the switch again. So, for now, don't even worry about the bottom loop. Just worry about the top loop. So, if the current's going in that direction, what's going to be the direction of the magnetic field around that loop? So,
Around the loop,
around the top loop, right?
like on the outside of the
On
loop.
the
or-
outside,
In.
so it's gonna be going out and then it's gonna be coming back in like this, right? Okay, everybody cool with that? You turn right hand rule. Boom, gonna go out, gonna come back in.
The
So
outside loop is not-
when the second loop is down here, when I close that switch, the current's gonna be going this way. So this bottom wire, right after I close that switch, what's that bottom wire going to sense?
Attraction.
No, do not get attraction into this. Just look at X's and O's. It's like football. We're just gonna talk X's and O's. Do not worry about attraction.
Okay.
So, I close this switch. Current's going like this. And that bottom wire, do you see where that bottom wire is gonna have a magnetic field that's gonna be coming up through the bottom? So from the bottom wire's perspective, are you gonna be having an increase in X's or dots?
Dots.
Why, Thatch? You're right. Why?
It's like coming up off the surface.
Yeah.
Oh,
So this is current is going this way. This magnetic field is going around and it's coming up like this. So from the bottom wire, all we're focusing on is the bottom wire right now. So that magnetic field is going to be coming up like this. So from the bottom wire's perspective, you're going to see an increase in dots. Okay? Increase in dots. So what's the bottom wire going to do to counteract that? It's going to make X's. So now, you're the bottom wire. You're sensing this increase in dots. You want to make X's. So what's the direction of the current then going to be in the bottom wire? So I got this. So is the bottom wire going to be in the same direction? Is the current in the bottom wire going to be in the same direction or the opposite direction? Opposite. Because I want this to go in this direction so that I can make X's to counteract that. So when I initially close the switch, current starts to flow. We're going to be generating this magnetic field. So temporarily in the bottom one, then it's going to create a current going in the opposite direction so that it can make X's. Now, is it going to do that continuously?
No.
Why? It's not. It's going to stop. It's going to happen very briefly. Why?
Because there's no change in the magnetic field after.
Beautiful. Because once the current gets moving, is the bottom wire still going to be in the magnetic field? Yes, but it's not going to be changing. So what you'll see is you'll see a very brief induced current in the bottom wire. But it's kind of like capacitors. Oh, after the capacitor has been, running for a long time, what happens to the current? It just stops. So the same thing's going to happen. Now, after a while, you would see a current in the bottom one, but then you would see it go to zero. But then eventually, I'm going to open up that switch in the top. So once I open up that switch in the top, what's the bottom wire going to sense?
A lot
Change in
of others.
magnetic.
A decrease in
O's.
a decrease in O's. Because now it's going, oh, I've lost my O's. Okay? It's got no dots because I shut off that current. So the magnetic field is going to shut down. So at that point, what's the bottom wire going to do?
Makes
Make a
noise.
flip direction.
Then it's going to make O's. So from the bottom wire's perspective, which direction does the current have to go to make O's in the bottom wire?
The other direction.
The other direction, right? Because of the fact that you're decreased, yeah, so the bottom wire, let me think this through. But yeah, so the current then is going to switch to the opposite direction to make up for the change. So what you would see, and this is another way that you can make alternating current. So if you flip that back and forth very rapidly, what you would see is a current in the bottom going back and forth rapidly because it has to compensate for either the increase and the decrease in the magnetic field. Makes sense. So this is how you can induce a current in a wire without having anything hooked up to it. Now, that it's not going to be a strong wire. It's like, oh, hey, I'm stranded out in the desert and my battery is dead in my car and I need to charge my phone. Oh, I'll get a battery hooked up to another wire and I'll make it. No, okay? Does it work? Yes. Is it really a good source of energy? Hey, not so much, but it works. Okay. Now, the last of the magnetic equations. Last of the magnetic equations, which would help if I had the right sheet.
Field area. Vector area.
Because you're talking about outside of it.
There's two different kinds. Maybe it's just
No.
the vector of the area is very
These are not that convenient.
Then it would just matter. It would just be area. You're still in just a regular, be another, like if you have a square, right? That travels in the direction of one side of the square, it's just a rectangle. When it travels in the other direction, it's a rectangle. Yeah, or a three-dimensional shape.
I can't wait to use quantum mechanics.
Or if it's not traveling necessarily in one straight line, but it's traveling in a changing line. Yeah, I think it's the area of decline model. Decline model area.
Ag surface area?
I'm sure there's a way to, but I don't know how to do it.
No, yeah, it is.
I kind of believe you, but look at how it can't be.
Yeah, the surface area is infinite, the volume is
Because it's an
finite.
impossible shape.
It's impossible in 3 dimensions.
Yeah.
Okay, except
I'll explain all this just a second. I can get all this.
Decline model.
and I would agree.
All I could hear was.
Look it up, it's impossible in 3 dimensions. That's like a threat.
Well, no, it's different if you want, but.
Bro, why not you
Why did I remember you guys said you would convert
There's nothing to be afraid of, bro.
I
Are you
used to try to convert everything.
There's nothing to be afraid of.
Everything can be inverted. It's just
Okay, I kind of wanna see somebody inside.
Okay, you wanna know something really
Like,
weird?
that would be
So,
really
I was telling my
This would
sister,
be
well,
interesting.
last night, I showed her
Why did you
the,
do
like,
that?
What would that
season
look
of
like?
season one episode.
Everything would just fall to the ground.
Oh my gosh, I need that.
Like, what would happen if you
No,
inverted?
same on episode
See how
4.
selfish he is?
Fighting the Guardian.
Yeah.
He doesn't care how he leaves it.
Well, no, because
Oh.
the
He just
inversion,
won't
you'd still have the same dimensions.
He doesn't care to leave it.
It would just be translated.
Bill, like in the old
Space.
Yes. Well, I don't think, we didn't go all the way. But like,
9,400, yeah. I got it.
but like when the Red Russians, I
Well, at least I'm not.
Jacob, what would happen if you inverted somebody? Like, that was the thing.
Even I didn't, the first time I saw that, I was like slightly traumatized.
And our chaos showed you
See your class colors?
I don't have a singular
What would happen if you inverted somebody?
I need to bring you
I must know.
like hold up, it was specifically for senior
Maybe Richard, you
That
body
bad.
page and we can paint his face
And I was
like
like-
a rally.
There's a pep rally.
Yes.
Wait, what's
3 months, do you guys
Wait,
do
does that mean I have to go to it? Like,
Yes.
That's interesting.
Oh, this is that
Probably
guy.
Aquaman is the best character
What
on
are
the
you, a
show.
toddler?
I'll do that.
However, and then immediately after I read that Johnny got killed, and I will definitely do the same. I just like can't do the same. I lost something.
What a Cohen thing to say.
Andy said we'll do it.
Hey, do you have homework?
Just say, he said.
Don't you have homework?
Yeah.
Okay. All right, now that I've got all that drawn out,
Flux.
You know how
Sorry, I just.
not to be confused with flux capacitor.
electronic?
Okay, so some people think this Greek letter phi looks like, if you know, like your Marvel comics, like almost looks like the symbol for the Green Lantern. Okay, basically it's an oval with an eye in it. That's all it is. So, and it has weird units because it's actually measured in levels. Okay, I don't know, it's just what it is.
It's measured in seals.
And it has kind of weird units. So you have a magnetic field measured in Teslas, and then you have an area measured in meters squared. So if you want to measure the value of phi, so, and again, we're gonna stick with the bracelet analogy. So this would be your cross-sectional area. B would be the magnetic field going through it, and then you have the cosine of the angle. Now, here's what's different about this. Every other one that we've dealt with has been sine, okay? This one is cosine, mainly because of the fact that we're dealing with the angle as it goes through the opening through the cross-sectional area. So what's the cosine? The cosine of 0? 1. So this is why when you talk about the angle, we're talking about the angle through like the central axis of the area, okay? Not the cross-sectional area. So imagine here's your shower head. The stream of water is coming through like this. So if that's your angle, okay, right, like that, so it's gonna be the angle with that central axis. So if it's coming in like that, you got the cosine is 0, which is 1. Now, the magnetic field is coming like this. If I turn it, where then this is at a 90-degree angle, then it's going to be 0. So with this one, you get your maximum flux coming through when the angle is 0. You get your minimum when it's at 90. which is in contrast to everything that we've done. Come and so help me God. Here's your choice. You shut that thing, I'm gonna launch it through the wall.
It's gone.
And I'm never gonna tell you that again between now and the end of the year, right?
Right.
15 more days. 15 days.
I'm sorry I'm not entertaining enough. I'll try to do better. So this is gonna be the angle as it comes through like this, okay? 0 to 90, when is the maximum, when is it the minimum? So typically, and unless you're given the angle, don't worry about it, okay? This is why most of the time when you see this, it's just your area times the magnetic field. Only if you have the angle do you worry about the cosine part of it. So here's the other side of this, is that, and your equation sheet gets real fancy, because they had this written as like the absolute value of B times the cosine of the angle times the absolute value of the area. It's the same equation. I don't know, they go through this, all of this deal to write it twice. It's just AB cosine theta, and most of the time you don't even worry about the cosine part of it. So that's just to calculate the magnetic flux, okay? Now, this is where the magic happens, is that if you're going to create a voltage, okay? If you're going to create a voltage, and it's the same idea. Notice that a voltage is going to be your change in your magnetic field per unit of time. Notice this is not flux per unit of time. It is change in flux per unit of time, okay? So this is where you get a voltage. You don't get a voltage if nothing is changing. And that's why I said there's 3 ways you can change that magnetic flux, okay? If you go with the shower analogy and the bracelet. So one is that you change the magnetic field. Oh, hey, you change how much water is coming out of the faucet. Is it barely on? Is it on full volume, okay? That's your magnetic field. That's your value. How much water is coming out. You can change the size of the loop, okay? Is it a small loop like this, or is it a bigger one? That's the one that's most difficult to realistically change when you go to change the area. You can do it, and we'll deal with that in just a second. Or you can move the loop. So you can move the loop closer, you can move it further away, you can turn the angle, and that's going to adjust that. So you can either change the water coming out of the shower head, you can change the loop area, or you can change the location of the loop itself. So this is where you get into a little bit of magic, okay? So the generic way of calculating this is that it's just change in flux per unit of time. So that means you either have to change one of 2 things. You either have to change the area, or you have to change the strength of the magnetic field. So if you assume that the magnetic field strength is constant, that means you're going to change some dimension. So what I did, and this is just going to show you how this goes full circle. So if you go back up here to this diagram, okay? So let's make sure everybody's cool with this. So you've got a wire in a magnetic field, and you have 2 dimensions. You have L, and you have a dimension of X. It could be A and B. I just put L and X. So I'm going to pull it to the right. When I pull it to the right, what are you going to see? More X's, more dots. You're going to see more.
X's.
So you need to make more dots. So to make more dots, which direction is the current going to move in the wire?
Up the
Up. So that way you're going to make more dots. So that you should be able to do without any thought at all. Okay, cool, got it. Take more x's. So when you're going to use this equation, you have two variables. You have the length of the wire that's in the magnetic field, and then you have the area, which is going to be the length times that value of x. Your L value will be a fixed value because you're not going to change the dimensions of the wire. That's set in stone. That isn't going to change. So if I rewrite this as change in x L over time, okay, that's all I'm doing. I'm going to keep the same magnetic field. So this is where you do a little bit of voodoo. You go, okay, cool. Well, if L remains constant, that's change in x per unit of time. Well, what do you get when you take change in x per unit of time? Velocity. Oh, all you end up with is magnetic field times the length of the wire times your velocity. And then that's going to get you your electromotive force or your voltage, depending upon how you want to write it. So all that, and again, it's the same idea. If it isn't moving, guess what? You're not going to get a voltage because there's nothing there. If you don't have a magnetic field, you're not going to get anything because there's nothing to change. And the L is just a fixed value. Okay, so how this plays out. If you can get this one, hey, you're going to be okay.
Should be testing your state. Yeah.
It's joules. Tesla meter square. Well, Tesla meter square. Well, maybe I don't have to do that. Is Newton per ampere? Which you can work with for other purposes, Mitchell. It's not, you aren't gonna write it like that.
If you take
It's
your
also
magnetic,
It's joules per
Area times.
I like Tesla's
It's not.
This is very much so calc. Actually, if you want to make calc, you can do parametric using also related time.
seconds of
Resistance.
Oh, because it's decreasing.
Wait,
But it's also testing your square.
wait, what are we talking about?
Okay, so imagine this. You've got a loop in a magnetic field. And we're going to decrease the magnetic field strength from 1 Tesla to 0.4 Tesla in 2 seconds. You've got the radius of the loop, 0.20 meters, which is fairly decent. The resistance of the wire is 0.010 ohm. Find the magnitude and the direction of the current. So let's start with the direction of the current. You have X's. You're going to decrease the magnetic field from 1 Tesla to 0.4. What's happening to the number of X's? It's decreasing, so you have to make
Because the field.
You have to make it.
You've got to make more X's, right? Because you're decreasing the number of X's, so you have to make more X's. So what's going to be the direction of the current? Is it going to be clockwise or counterclockwise? Clockwise. So the current is going to be going in that direction so that I can make more x's to compensate for it. Okay? So, if you look at yonder equation sheet, so what you have, and this is all you're going to have on the test on Monday, is you go, okay, right, I eventually want to find the current. Bergkamp gave me the resistance, and I want to find the current. So what's your ultimate end game equation where you want to end up in? Yeah. You want to vert it up. Okay? So I've got the resistance, nowhere is there, but what I need to find is the voltage. Voltage is the same thing as your electromotive force. Same thing. So again, if you look at what you have on your equation sheet is you have E equals changing your magnetic field over time. But your magnetic field is equal to your area times your magnetic field over time. So, can you find the area? Yeah, it's a circle, pi r squared. That's a fixed value. You're not going to change that. That's a fixed value. So, you're going to have a constant area times the change in the magnetic field over time. Now, this is an absolute value, so don't get wonky and go, oh, you're changing it from 1 to 0.4, and that's a negative value, okay? It is, but you're taking the absolute value of it anyway, so it really doesn't matter. So here's the point. So you're going to have pi times that radius of 0.20 meters squared, and then you're going from 1 to 0.4, which is going to be 0.6 Tesla over 2 seconds. And if you do all this, you get .0377 volts, okay? Which isn't a lot, okay? But again, it's a relatively strong magnetic field, and so there's your voltage. So from there you can vert it up and take that 0.0377 and divide that by volts, 0.010 ohms, and you get a whopping 3.77 amps. Now, the problem is that's going to be very, very short-lived, mainly because that's only going to happen while the magnetic field is changing. So for those of you that are studying calculus or going to take calculus, you spend a lot more time with calculus on electromagnetic things because you have a lot more things that are changing. So you can get into, what's the rate of change of the magnetic field? And, you're much more likely to use calculus on the electromotive side on it as you are on the mechanical side of it. Okay. I'm done. My voice is dying.
It would make sense to use mechanical impedance rather than rail. I swear. I need that now, but I think it makes sense.
Yes.
Yeah, imagine both you take this entire class again and do calculus.
That would make it easier, though.
No, all the deltas will be
It's all calculus.
Yeah.
That would not make it easier. If you related rates, it's not even really that bad. Just calc 1.
Cohen, don't you
Or
have
unless you want
homework?
to write parametric functions for it, because then you'd really need time. But
Don't you have homework?
I don't know what he's blabbering about.
So you know how the center of the bike there's a bearing, right? Basically the idea is that you remove that so the wheel revolves inside the wheel. So it's basically a bike wheel or a bike without the middle section.
Make sure on questions 4 and 5 that you do like greater than, less than, or equal to. Do not do commas.
Aww.
On number 6, when you have to draw a graph, this will make sense when you get to it. Pay attention to where the graph starts and how much time is going to be involved. So on number 6, you're going to have a graph where you're going to have time here, and your magnetic field is going to be, or actually, I think they give you the graph and they ask you questions about it. So, all right, I'm done. You're on your own.